Now, this whole idea of doing a Taylor polynomial to approximate a transcendental function or an algebraic function brings us to the idea of our error. How much are we off? We should be able to figure out, if we do an approximation, we should be able to approximate in turn the maximum amount that we're off, our maximum error. And we do that with the idea of the remainder. Now we know that f of x is the true function minus the polynomial. That's going to give me what's left, or the remainder. So we use this notation r sub n of x to represent the remainder function. The remainder for f of x, having approximated it by Pn of x, the Taylor polynomial. And that brings us to what's known as Taylor's theorem. So let's f have a continuous derivatives up to the n plus 1th derivative. So if I do Pn, I need one more derivative beyond that to be continuous. On some open interval containing a. Remember, we're going to approximate about a, so this open interval really represents this area that we're going to be approximating within. For all x in the interval, f of x will be equal to this polynomial approximation plus the remainder. It's from here that we get this idea. And this remainder is actually equal to the next derivative over n plus 1 factorial times x minus a to the n plus 1. But notice, rather than evaluating this at a, this is evaluated at c. So c is some value between, I'm going to say x and a, where a is a known point and x is what we're trying to estimate. Say estimate at x. So like that example I did with square root of 10, a was 9. I knew square root of 9, so x is 10. So c is some value on that interval. Now, since this value of c is typically not known, we don't know what value on there to actually pick, we're going to estimate the bounds. We're going to try to figure out what the maximum bound is going to be for this guy, and we're going to think about it in terms of absolute value. Because the error, we can always think of as an absolute value, because that tells us how far off, but not necessarily in what direction. Now, assume it's possible to do to begin with. This following theorem actually gives us a standard estimate for the remainder term. In other words, we're going to figure out reasonably what this maximum value could be. So, the estimate for the remainder, let n be a fixed positive integer. Suppose there exists a number m such that the nth plus 1th derivative evaluated at c, this unknown value, is going to be less than m. So m is like this upper bound for all c between x and a inclusive. Inclusive simply means I can include the boundary points. The remainder of the nth degree Taylor polynomial for f centered at a, this is that known point again, is going to satisfy the following. The absolute value of the remainder polynomial is equal to the absolute value of f of x minus the nth polynomial, nth Taylor polynomial, which is going to be less than or equal to some value m, this upper bound, times the absolute value of x minus a to the n plus 1 divided by m plus 1 factorial. What we've done here is we've taken m and we've used m to replace the nth plus 1 derivative at c. Now, one reasonable approach to try to figure out m, which is kind of commonly seen in a lot of textbooks, is to try to maximize this. This is just a function. If I make this a function of x, to try to maximize this function, which means take yet another derivative and try to maximize it over this interval, either x to a or a to x. Now, the problem is that this commonly results in the value you're trying to estimate. So if my function, if I have something that's monotonic like this, and let's say here, and this is my known point A, this is the value, right here is the value of x, so I'm trying to estimate this value, and I'm going to take the derivative and I'm going to maximize it over this interval. Well, if this derivative is linear or quadratic, if it's monotonic, it will maximize when x equals a. So that won't work because that's what I'm trying to estimate. And if I knew that, then I wouldn't have to be doing this to begin with. So what we often do is simply reason out what this upper bound may be. See, if this is a sine function, I know the biggest that sine gets is going to be 1, and the smallest that sine gets is going to be -1. So I know that m can be no bigger than 1 and no less than -1. But m is greater than the absolute value, so I'm only going to be interested in a positive value, so I'd put 1 there. If it's some other function, then I may know what this function is at a, and I may know what this function is at b, and I know that f of b is greater than f of a, and I know then it's monotonic, so then f of b must also be greater than that. So now I have an upper bound that I could use. So that's the type of thing we commonly do. So we commonly must reason out a value for m. Now, obviously, we could reason it out as being really big, which should be kind of silly. This would still hold true, but if we're going to use this to try to figure out, well, one thing that we can do is try to figure out what value of n we need to get in order to get within a certain value. So let's just say, as an example, I wanted to make sure that the absolute value of what I'm thinking of as my error, I want to make sure that is going to be no more than 0.001. That means 0.0001 is going to be no more than m times x minus a to the m plus 1 over m plus 1 factorial. Well, x is going to be the value I'm trying to estimate. So in my previous example, a was 9 and x was 10, so this is 10 minus a, 10 minus 9 to the m plus 1, which is no big deal because that's just 1, over m plus 1 factorial, and then this value of m is going to totally decide what n is going to be, so that it's no more than 0.001. And this may not be something that you can simply solve algebraically. You just may be trial and error by looking at different values of n. You can quickly get to where you need to be. Keep in mind that, or don't lose sight of the fact that when I do this, so right here, this is an upper bound for my error. It's not really an approximate for the error. It's an upper bound. I'm saying I'm quite confident that the error is no more than this.